Hello, everyone. Welcome and thank you for joining the Boston University Institute for Sustainable Energy for the second workshop in our series, Where is Energy Storage Headed? And for this session, we focus on interfacial phenomena in electrochemical systems. I'll be the moderator. I'm Sahar Sharifzadeh, Associate Professor in Electrical and Computer Engineering and Material Science and Engineering. Wally, are we going to have the slides put up? Okay, yes. So it's my pleasure to be joining ISC, who's partnering with the College of Engineering and the Division of Material Science and Engineering for today's webinar. All of ISC's research on energy and water systems, sustainable cities, sustainable finance can be found at bu.edu/ISC. So for today's workshop, as I mentioned, we're interested in interfacial phenomena in electrochemical systems. So complex multiphase interfaces are central to many electrochemical systems performance and longevity for many energy applications, such as what you'll be hearing about today. The fact that these interfaces are dynamic, combined with the complex chemistry that occurs during the operation of the device, has made understanding and, importantly, designing the interfaces of these systems challenging. So in this workshop, we're going to discuss the formation of interfaces and interphases and their effects on performance. Both for understanding the physical phenomena at interfaces and also the advances that are needed to design better interfaces. So today we'll have three speakers. I think they're, Ollie, I think they should be, if you can go to the next slide. Okay, thank you. So we have Veronica Augustine, who'll talk about electrochemical energy storage and reactivity under confinement in layered materials. Thomas Senfel, understanding interfaces in electrochemical systems with atomic simulations. And Irina Zenyuk, who talk about electric double layers at catalyst electrolyte interfaces, understood from electrokinetic phenomena. First, we're going to have Veronica Augustine. First, we're going to have Irina Zenyuk presenting. So she's an associate professor for chemical and biomolecular engineering at the University of California, Irvine, where she's also associate director for the National Fuel Cell Research Center. Her group works on enabling solutions to challenges in energy, specifically low temperature hydrogen fuel cells, lithium metal batteries, and electrolyzers. So Irina, please go ahead and start.
All right. Thank you, Sahar, for such a nice introduction. And today I will talk a little bit about different combination of topics, because I realized that the field understanding buried interfaces is really important, and there's techniques that are currently used. There are a lot of techniques, but there are few techniques that are kind of underutilized. And today I just want to talk about few characterization techniques that can be better utilized in electrochemical community. And these techniques will be discharged optical emission spectroscopy, glow discharge, so this is GDOES, and I will also talk about X-ray computer tomography. So my talk will be more focused on electric characterization techniques rather than systems we study, and we study electrified interfaces. We study those applied in fuel cells, electrolyzers, and batteries. So I will start first by introducing where I come from. So I'm associate professor, University of California, Irvine. We are a public university located in South California. Our campus is beautifully located close to the some of the best beaches in the United States. And if you come to think of us, we are famous for our sustainability efforts on campus. So we really take electrochemical systems seriously. We deploy them on our microgrid. We study them through National Fuel Cell Research Center. And most recently, we found Horiba Institute for Mobility Connectivity, where we can take actual devices and test them in large environmental chambers, or put devices on dynamometer and cycle them. And this is Professor Voja Stamenkovic was hired as the director of this facility. So the overview of the talk, I'll introduce you to the glow discharge optical emission spectroscopy technique and present you some of the capabilities, what it can do for buried interfaces in batteries, and why we should pay attention to this technique and what's been done before. And then I'll transition and talk a little bit about X-ray computer tomography and how it can be applied again on buried interfaces and using operando studies that we've already done. So overview. What is a glow discharge optical emission spectroscopy, and why should we use it? Well, it has a large potential to be utilized in research of battery systems and battery interfaces. What you can do, you can measure a depth profile of elemental distributions in any material. So if you have a layered material that has buried interfaces, this technique can sputter away material and give you resolution all the way from millimeters to micrometers to nanometers. So it's a multi-length scale resolve technique. And it can also, it's sensitive to all the elements. So you can detect all the elements all the way from hydrogen to uranium. You have to have active plasma to do that. It's fast, it's easy to learn, it's a high throughput, so you can go through a lot of samples in a short time, and it can also analyze non-conductive samples. The drawbacks is that your samples need to be films, so thin films. For batteries or fuel cells, electrolyzer is perfect, because usually we are working with film type of samples, and this technique can probe those interfaces quite well. In terms of what is glow discharge optical emission spectroscopy, I think in our field it has been used only by very few groups, so I really would like to introduce it first. So this is a diagram of what the process looks like. So first, voltage is applied between anode of GD instrument and the sample. So we have a sample here, you have the anode. And then it must be conductive if you want to do direct current glow discharge. And electrons flow then from electrode with a positive potential to the other electrode with negative potential to the other with positive potential. And the chamber is filled with argon gas. So electrons that are accelerated by potential difference excite this argon gas to form plasma, consisting of positive ions, neutron particles, and free electrons. So in the next step, the positive ions of the plasma then are attracted to the negative electrode. And in this case, essentially they they have sufficient energy to knock atoms off the surface. So that's what happens. That's how we sputter away the sample. And this is, and then from there, sputtered atoms, they are excited by collisions with free electrons in the plasma, and then these elements de-excite, and as they de-excite, they emit light at certain characteristic wavelength. And then this characteristic wavelength is then detected by spectrometer, and this way we can detect all the elements that are present in this interface and in the bulk material of the cathode or the anode or the combined battery, for example. So this is an example showing state of charge of 0 of the battery. So the battery is fully discharged, and you can look at the distribution of the elements in the cathode of standard NMC type of electrode. And once we sputter away, this is full thickness, then we reach aluminum current collector. So what's interesting here, we can detect interfaces which are nanometer size, because we can really slow the process down and resolve species spatially through these nanometer domains, and then sputter away into the thickness of the electrode and detect all the other bulk elements. So this is just to provide you the overview of how the process works and what type the final signal that we receive, it's in volts. So we need to convert this into the atomic percentage of certain elements. So if we think about what's been done in batteries field using low discharge optical emission spectroscopy, the group from Japan is very active in this field, and they looked at the quantifying lithium in lithium-ion batteries, and they looked at the lithium with varied state of charge. And you can see here, this is pristine electrode, and this is going from 0 state of charge to all the way 100% state of charge. And they also did the same thing for NMC and for the carbon anodes as well. And what's interesting, this is a group that is really active in this field, and you can see that it's really well resolved, and the profiles, and we can see these local fluctuations as well, and then we can also detect things that happen at interface. And this is the most interesting phenomena, because if we are to probe solid electrolyte interface with this method, we really need that nanometer resolution. And so if we are to look at the another group that works in this domain, you can see that they probed lithium metal plating on the anode when in the lithium-ion battery, and they were able to quantify the amount of lithium deposited. So this is a destructive process, but one can actually extract like separator and the anode together and sputter away both separator material and anode if one is looking into that interface, for example. So it's all possible to look into actual those buried interfaces. So that's what's been done before. So what is one trying to answer using this? What type of questions one would like to answer? So in terms of modeling efforts, a lot of groups still use Doyle-Fuller-Newman model, right? And that type of model can predict the concentration of lithium in the anode and cathode versus various drive cycles or cycling profiles. And that's one of the motivation to validate the model, because we can really use the GDOES to tell us how much lithium is at any stage or during the cycling, right? And then another possibility is to use the low discharge optical emission spectroscopy to probe the solid electrolyte interface. So just to understand its chemical composition under different chemical conditions, under different cycling conditions. And obviously it can be cross-correlated with various other techniques currently used. For example, XPS for also another elemental detection technique, surface technique, and ICP-MS just is used heavily to actually calibrate the tool, because we get voltage, we do really need to get into atomic weight percent, and of course X-ray computer tomography, which can be used as non-destructive operando tool and can tell us the morphology of the layers and buried interfaces that happen at both nanometer scale, nano CT, and micrometer scale, micro X-ray CT. In terms of calibration, it's interesting because, of course, there are a lot of calibration samples one can purchase. Those are usually very expensive, and so we came up with kind of neat alternative ways to using different stainless steels that are available, and they do have different content of iron, molybdenum, nickel, cobalt, and those are the elements that are much needed to calibrate, for example, this instrument for the cathode materials of the lithium-ion batteries. And using XRF, we can get a weight percent of elements in bulk material, and we can also use ICP-MS to get more in-depth calibration. So if you look at on the calibration curves, this is the type of profiles we would get from the low discharge instrument. So you see at the interface, there is some interfacial phenomena happening here. So the surface was the composition of the surface different than the bulk. So you can see that looking at various stainless steel, we can create really nice calibration curve for nickel. So this is weight percent versus signal of glow discharge in volts for molybdenum, and we also can do that for cobalt. So it's kind of neat way to calibrate the instrument. But for lithium, the problem obviously is that hard X-rays are insensitive to lithium. We cannot detect it using X-ray fluorescence, for example. So obviously ICP-MS must be used to calibrate lithium curves. And the goal, as I mentioned already, to use that result GDOES to study lithium distribution under different cycling conditions. So how does the cell look like? So if you think about transferring the sample from the glove box into the instrument, we have one needs to have this airtight environment. So there is a sample holders for that. Typically, the sample will be mounted by conductive tape onto the sample holder, and typically this crater will be created. You can see here it's about 3 millimeter in diameter, and this is where the sample was sputtered away. And you have liquid cooling by nitrogen, because otherwise this will overheat. And so the sputtering, depending on the resolution one wants, the sputtering can go for a few hours or 10 minutes. So with higher resolution, we need longer time. So usually 6 hours for nanometer resolution. So what do we expect to see? If you think about obviously battery typically being discharged or charged at 0% state of charge, we expect to have high lithium content in the cathode, and at 100% state of charge, we expect low amount of lithium in the cathode. And so looking at the profiles that one can obtain from during cell being discharged from the pristine sample, and here time correlates roughly to a micron resolution. So you can see here within 1 micron we collected a lot of information, and you can see that actually you see the steady state achieved lithium profile achieved somewhere after 3 microns or so. So as you can see, as state of charge increases, you can see we have less and less lithium present in the cathode of the material. And it's interesting, the dynamics change too at the interface. So I think what's the most interesting part of this is actually zooming into this area here to show what is that, how does at the interface lithium concentration changes, because in bulk we can predict obviously using standard classic models, but the interface is definitely much more complex, and currently we're still trying to investigate this behavior, this peaking at the interface, and whether maybe there was some lithium plating or something happened here that caused this peaking at the interface. So overall, just to conclude, glow discharge optical emission spectroscopy is an amazing tool for studying buried interfaces and for studying understanding lithium distribution in bulk materials, and also understanding all interfacial phenomena. And in this case, we applied it to the lithium ion batteries, the cathode materials, and looking into the what this can be correlated to, and our group does a lot of X-ray computer tomography, which is we applied mostly to the lithium metal batteries. So if you think about classic lithium ion battery, currently we have graphite electrode as the anode, and then if we want to go to the higher energy density batteries, we have gravimetric energy density batteries, we have to move into direction of lithium metal. And eventually we want to get rid of lithium metal and have the lithium metal free type of anode batteries, where all the lithium is stored initially in the cathode material. So how to achieve that? Well, the major problem is that as we charge the battery, we form this trees at the interface, which called dendrites, and this is something that the problem is in solid state batteries, whether you have polymer or whether you have some ceramic type of separator. Those dendrites will be growing on lithium metal. So there is a lot of science currently of how to stabilize this interface. So what we do, we are looking at operando cells using X-ray computer tomography. And in this setup, you have X-ray source. You have your battery on rotating stage, and you have the X-ray detector and other optics along the way, depending you use nano or micro CT technique. And from there, you can put just the real battery, but then you're not going to see much interfaces. So you need to design the sample holder very well for that. And X-rays are sensitive to most of the elements, but lithium is very light. So there is a challenge of how do you detect lithium with hard X-ray source. So it turns out we can do it in phase contrast mode. We can also, because the lithium is so light, it still will stand out on the backdrop of, for example, of polymer electrolyte. So if we are to look, for example, at typical plating profile, you can see that this is lithium metal anode, this is polymer electrolyte, and we are looking at charging and discharging, so plating lithium and stripping back. So what you see here, you see first forming this, this is around 100 microns, so this plating layer is around 20 microns. So you can see here plating and then stripping back, and you see a lot of that and dendrites left on the surface. So this technique is quite powerful in doing this operando studies. So for example, looking at this interface from different direction, you can see almost solid film is being built, and then it's stripped away, and you can see it's almost like the lithium behaves almost like a fluid at this interface. So it's you have, of course, you have the dendrites, but you have also this lithium forming like almost liquid film. And then when you strip it back, it strips back, and you can see it moves at the interface until and it's being some of the dead dendrites are being left, and some of this film is being left. So it's a really interesting phenomena. And if you think about sample holder design, this is what we currently use. It's a coin cell within the pouch cell. So active area is around 1 centimeter diameter. And with X-rays, we can really probe this area in operando. And this is actual pouch cell, because a lot of limitations in the field currently, because building swage lock cells, you really need to have perfect alignment, perfect compression. And having just regular pouch cell, you can create many of them, we can image them quite easily. So actually going closer, like moving away from swage lock cells into pouch cells can enable much more capabilities when it comes to X-rays. So typically, then the next step is how do we quantify the data? And quantifying data is another challenge in the field, because if you think about these interfaces, they are not so clean, right? So you have, this is lithium symmetric type of battery that has been cycled. And this is polymer electrolyte here in the middle, and you can see that you have the dendrites on the interface. You have some layer that has combination of pits and dendrites, and quantifying this interface needs first step of thresholding, essentially separating what is dendrite and what is not. So in this sense, we are developing machine learning algorithms to do that, because if you look at this typical dendrite, for example, it has a lot of grayscale variation across. So you have very bright edges, and you have the pits, and this is because of phase contrast artifacts that come when you do imaging X-rays. So this is how one would segment when you have undergraduate students spending hours manually coloring each pixel. So this is ground truth, and this is what different machine learning algorithms are currently predicting. So you can see that we really need more precise. Some, for example, this UNet and YNet do have higher precision than the other two. So this is in collaboration with our partners at the Berkeley lab. To quantify the data, we do need better machine learning algorithms currently. So in summary, X-ray CT tool is quite powerful when it comes to exploring buried interfaces and exploring operando devices, and especially it's sensitive to lithium metal. If you design your cell well and you design your components well, you can see lithium, and that's and lithium metal, and that's kind of the advantage. And so I want to finish my talk here and thank my group and thank the Horiba Instruments for their support, and also our team and Advanced Light Source beamline scientists who helped with imaging.
Okay, thanks very much, Irina, for the very interesting talk. So I have just one question for you. So it looks like you're able to see the sort of time evolution of that dendrite growth, right? Would you be able to sort of zoom in time and see exactly what sort of instigates that growth? Like what kind of defects, what's their geometry, what's their chemical structure, and so on?
This is a very good question. Yes, the nucleation and growth, it's a big, big problem, and we want to investigate it. So typically, scan time takes about 3 minutes. So technically, this process of plating is quite slow because in batteries. This is when we talk about 1 milliamp per centimeter square, 3 milliamp amp hour, some C rates like this. It's pretty. We're talking about few hours or hour of charging, an hour of discharging, and so yes, technically we do have this transient data and trying to understand nucleation. We try to build a lot of different correlations with defects in lithium metal anode, with the whether plating and pitting correlate, whether there's defects in the membrane. Currently, we don't see any good correlation. So to me, what it looks to me, it might be on the more on nanoscale, some of these defects and some of this oxidation state of lithium. So we really need to look more with probably correlate this to TEM or some identical location that can probe those higher resolutions that we cannot.
Okay.
Thank you.
Okay, well, thank you for the talk, and we'll hear more from you, I guess, at the end of the session. So our next speaker is Thomas Senfel. Tom is an assistant professor in chemical and biomolecular engineering at Rice University, and his research focuses on the development and application of computational modeling tools for assessing complex multi-component materials, such as what he's going to tell us about, for the rational design of systems for energy conversion, storage, and utilization. So please go ahead, Tom.
Hey, thank you very much for the introduction and for the invitation to speak today. I'm very excited to tell you about some of the work my group has been doing, developing atomistic simulation tools to understand materials in electrochemical systems. And today I'm going to talk about understanding battery materials in particular. So I'd like to begin by acknowledging everyone who was involved in the work. In my own group, all of the simulations that I'll talk about today were done by Manav Bhatti. And all of the experimental work that I'll discuss today was done by our collaborators, Professor Lisa Biswal's group, and her student Kwan did all of the experiments. So we're interested in applying simulation to design better anode materials in batteries. And here I've just highlighted a couple of the common anode and cathode materials. And I want to point out, we're very interested in silicon because it has a theoretical capacity that's almost 10 times that of the current state of the art, which is the graphite materials. But the challenge is that silicon undergoes a very rapid and large volume expansion upon lithiation. So you can get a lot of lithium into the silicon, but then the silicon expands, and that causes quite a lot of problems. You have large volume fluctuations, large stress fluctuations, and ultimately that destroys a lot of the interfaces in your electrode material. And it leads to a host of problems that really cause the electrode to fail very quickly. So we want to effectively use simulation to understand what's happening at these interfaces, to understand how we can potentially mitigate some of these stress fluctuations and the stress buildup so that we can have stable interfaces and really enable the use of this high capacity silicon material. And the strategy that we're gonna take is to take the silicon and embed it in a polymer. And this is a strategy that's been around for a while. In particular, we're going to talk about a system that was discovered or developed by our collaborator, the Biswal group, where the idea is to have mesoporous silicon that's embedded in this polymeric binder. The idea being that when the silicon expands, it has somewhere to expand to, right? And if the binder is sufficiently flexible and elastic, then you can effectively mitigate that volume expansion in the collective electrode, even though the silicon itself is going to expand. So just to see this at the experimental microscopic level, what I've shown is a micrograph of the mesoporous silicon electrode, again, developed by the Biswal group, without any binder. And we see that after a couple of cycles, it fractures and you really lose the interface. The material degrades really quickly. If instead you embed the silicon particles in a polymeric binder, you can cycle it several times and maintain a nice structure, okay? So this is the goal. We want to understand what properties of the polymer, in this case, pyrolyzed polyacrylonitrile, are responsible for effectively maintaining the structure of the electrode. And what the Biswell group showed, effectively, if you compare the performance of the electrode over several cycles of the polymer binder composite to the just pure silicon, clearly the pure silicon fails rapidly, but the binder is quite stable. So what does this interface look like? That's the key question. So we have our binder, we have our silicon, and if we just look at the cartoon form, we know the silicon is going to expand when we lithiate. It's going to expand into the binder, and there's going to be all kinds of chemistry happening at that interface, right? So if we zoom into that interface, we have our silicon material, we have our polymer binder. There's specific bonds that are forming at that interface that really are going to control the behavior of the electrode. And this is where the atomistic simulation comes in. We want to go from this sort of macroscopic picture to the microscopic picture so we can understand how we can design the binders at the molecular level to optimize performance to really stabilize this interface. So today I'll talk about the comparison of three different binder materials. This pyrolyzed polyacrylonitrile, and polyaniline. And we're going to look at the different properties that each of these binders have, and we're going to assess these properties using atomistic simulation tools. Among them, the ones that are important, the binder has to adhere strongly to the silicon surface, otherwise the silicon particles can migrate around and agglomerate, and you lose surface area, you lose the effective active material. The binder has to have good ionic conductivity. Lithium has to be able to get into and out of the material. It has to have a high elasticity because the particles are going to be expanding into the binder, so you don't want to confine the silicon too much so that it can't expand upon lithiation. Of course, it has to be chemically stable at whatever potential we're operating at. And there has to be some degree of electronic conductivity as well. So how do we use simulation to understand all of this? And ultimately, it matters because the three binders that we're going to look at, they don't behave the same, right? Their performance is drastically different. The pyrolyzed polyacrylonitrile really does a good job of stabilizing the silicon. Polyacrylonitrile doesn't work as well, and the polyaniline completely fails. So we want to understand why this is occurring. So it all comes down to the interaction between the polymer and the silicon surface, and ultimately the behavior of the interface. So we want to know what types of bonds are forming, how many bonds are forming, are various chemical reactions happening, is the polymer breaking down? Once you introduce the electrolyte, is that going to also be breaking down and generating new species at the interface? All of this is going to control and influence how the interface performs ultimately. So we want to know what's the structure of this interface, how well does the polymer bind to the surface, and then how well can ions and electrons transport themselves through the material. So if we want to answer these questions, what we want to first understand is what simulation tools can help us to understand interfaces. So if we look at the sort of classic choice of scales for different simulation tools, we could start with quantum mechanics, which of course is the highest accuracy that we could get. We can explicitly understand at the electronic scale what is happening in the system. The downside is the computational expense. And that means that we're going to have to limit our system models to things that are on the order of a few hundred atoms. We could get away with periodic boundary conditions to model an interface, but it's going to be a highly idealized picture of what the interface looks like. And it's not going to capture a lot of the variability that we know is existing on these interfaces in real devices. We could turn to classical mechanics, so-called force field methods, which allows us to scale up the size of our system and scale up the time scales that we can understand and study. The downside is classical mechanics are not designed to handle chemical reactions. So usually we have to predefine all the bonds in the system so we can allow molecules to move around and stretch and bend, but reactions aren't really going to happen, or they're not going to be described well if we restrict ourselves to just classical mechanics. So if we want to understand bond formation at the interface, one option is to turn to what's known as a reactive force field. And in particular, the flavor of reactive force field I'll discuss today is called ReactFF. And the idea is ReactFF builds into its formalism some description of chemical bond formation. And that allows us to get away from the computational expense of quantum mechanics, but also look at binding interactions that are occurring at interfaces with a quasi-classical picture. So today I'm going to discuss the functional form of ReactFF in some detail. Since it's a workshop, I want to give everyone a pretty clear picture of how ReactFF operates. And then I'll illustrate how we can use ReactFF to understand the silicon polymer interfaces, and really ultimately to understand why the PPAN binder outperforms some of the other binders that are out there. So just to review the idea of a force field when we want to simulate a system, I'm showing you here a classical force field where the idea is to decompose the energy of the system into a sum of energy contributions that we can write a closed compact functional form to describe. So for example, if we have a bond in a molecule that's stretching, right, we could approximate that simply using something like Hooke's law. So we have a harmonic potential that describes how the energy of the system goes up when we stretch a bond away from its equilibrium position. We could do the same thing to describe equilibrium angles between atoms, equilibrium torsion angles as well between atoms. So you can see that the model is very simple from a computational perspective. These are not expensive equations to handle, so we can scale up the system to really large sizes. Of course, the problem is we've completely lost any description of electronic effects, and the biggest electronic effect that we're missing is bond formation, right? We can stretch this bond, the harmonic potential is never going to allow that bond to break, and that's why we need a reactive force field. So this is an overview of how ReactFF decomposes the energy contributions, and the key feature of ReactFF is that it builds in this bond order function to describe bond formation and also to describe all of the energy contributions that would be dependent on whether a bond is present in the system or not. ReactFF also includes things like Coulombic interactions and polarizability, so we can have charges changing as the simulation is progressing, non-binding van der Waals interactions between molecules, so things like polymers that are interacting through van der Waals would primarily be described by this term in the force field. So the bonding interaction is defined by a simple function that counts the number of bonds that an atom is making based on the distance to the neighboring atoms around it. So a simple example would be if we had two carbon atoms, as we bring them closer and closer together, we have a function that counts whether there's a sigma bond, a pi bond, a double pi bond. So the total bond order, which would be the contribution of all three of these, goes from 0 when the two atoms are far apart, all the way to 3, right? So we have a triple bond when they get close. If we change the atom type, for example, if we had hydrogen, we simply wouldn't allow the pi bonding and the double pi bonding to occur. So we could only have a bond order of 1. So we have a simple functional form that predicts whether there are bonds between the atoms. And then we recast the bond order dependent terms as a function of the bond order, right? So the bond energy, so this well, is now a function of whether or not there's a bond between the two atoms. And this allows us to really understand how the other angle terms and torsion terms would be dependent on whether there are bonds in the system or not. So taking a simple example, if we look at a water molecule, right, a classic potential would describe this angle energy the same irrespective of what the bond distance is between the oxygen and the hydrogen, right? So if we elongated these bonds, right, the stiffness of that angle would stay the same. And we know that this physically is going to break down as we would break that bond, right, the oxygen and the hydrogen. That angle should no longer contribute anything to the energy of the system, because if it's not bonded, there's no longer any angle strain. So we recast the angle term as a function of the bond order, and we choose a functional form that effectively weakens the harmonic potential as the bonds start to dissociate. So in essence, the molecule becomes less rigid, right? And ultimately, as the bond breaks, the angle contribution completely flattens out between these atoms, and that allows us to naturally describe bonds forming and bonds breaking. I also want to mention that we recalculate all of the charges in the system at each step of an MD simulation using a charge equilibration scheme. In electrochemical systems, this is, of course, very important because the charges are changing. You need a polarizable description. Without getting too much into the details, effectively, the way that the method works is that we minimize the electrostatic energy of the system with respect to the partial charges on all of the atoms. That allows us to basically solve for the optimum partial charges of all the atoms in the system to minimize the electrostatic energy in the system. And we can compare that to what the explicit charges are calculated at the DFT level or the quantum mechanical level. So this allows ReactFF to describe kind of polarizability, and it allows us to update the partial charges as bonds break and form. If a water molecule dissociates, right, it needs to dissociate into a proton and a hydroxide, not the two neutral radicals. And this charge equilibration scheme enforces that. So the other feature of ReactFF is the transferability of its parameter sets. And this is just an overview of some of the kind of diverse types of systems that ReactFF has been developed. And I just wanted to highlight a few of these where the interfaces are particularly important. So ReactFF has been used to look at gas-solid interfaces, liquid-solid interfaces. So really, it has a diverse and transferable functional form, which really makes it ideal for studying electrochemical systems. And that's why there's a lot of studies that have applied ReactFF, particularly in the battery literature. I've highlighted a few of them here, just in case anyone in the audience wants to follow up with these references and are particularly interested in any of these phenomena. ReactFF has been used to understand electrolyte decomposition and SEI formation on interfaces. It's been used to understand lithiation and delithiation of silicon, sulfur, as well as lithium transport through electrolytes, solid electrolytes, liquid electrolytes. And it's really a very powerful tool for looking at these dissimilar phases. Okay, so let's get back to the application. Now that we have this tool that allows us to describe interfaces, let's see if we can use it to understand how the polymer silicon interfaces are behaving in our composite electrodes. So we'll start with just the simplest case of putting one of the single chains on the silicon surface and see what bonds form, see how the chains are behaving. And what we find is there's a clear difference in the binding behavior of the p-pan compared to the pan and the polyaniline. P-pan binds almost entirely through the nitrogen lone pairs, and it really stands up. Whereas the polyaniline lays flat, you have a lot of carbon bonds as well as the nitrogen bonds. And pan binds primarily through the nitrogen groups. You can see that the pan really curls up. It doesn't stand up straight, just some characteristics that we can observe about how a single chain behaves. And we can see that the strongest binding comes from this polyaniline. Okay, so that would suggest that polyaniline might be the best if we want strong adhesion between the polymer and the silicon surface. So the next thing we did is, let's look at the way that an actual bulk binder interacts with the silicon surface. So here we do the molecular dynamics to properly relax the system, allow the interface to form, and then we compute the interface energy, effectively the energy required to break the interface between the silicon and the polymer. And we see something surprising. Polyaniline, where the single chains would bind the strongest, binds the weakest if it's in bulk form. So we get this reversal in the trend of the binding energy. And we see that if we run the simulations multiple times and we take statistics to make sure it wasn't just an anomaly based on the way we initially had set up our system, this trend reversal is very robust. Okay, so we see that if we look at the single chains, p-pan binds the weakest, polyaniline binds the strongest, exactly the opposite trend if we look at a bulk polymer at the interface. So, what's going on here? So we analyze the interface. In particular, we analyze the way that the polymer is binding on the interface. So the first thing we wanted to look at is the orientation of the chains. So we simply defined an angle based on the normal of the plane of the ring. And if we look at that angle as a function of kind of where the chain is in the system, we see that near the interface, here the purple is after we've run the simulation, the green is at the beginning of the simulation. Right, just to orient you here, we're talking about the interfaces. We see that this angle really starts to go to 90 degrees towards the interface, and that is reflecting the p-pan's tendency to bind kind of straight up and down to form this vertical. That doesn't happen with the polyaniline. The polyaniline actually broadens, right? It wants to bind flat. So this matters if we start to count how many chains are bound to the surface, right? If we look at a distribution of just the number of rings bound onto the surface, we see that p-pan has these large spikes, meaning a lot more chains are getting down onto the surface. The polyaniline, we get a little bit of kind of spikes at the surface, meaning there's more chains that are bound there. But because it's binding flat, you basically get really strongly bound chains that block all the other chains. So the picture that emerges is that although each individual chain of p-pan binds weaker than polyaniline, you get a lot more of them down on the surface because they can stack themselves up. If we go and look at the experimental system, these are micrographs, again, from our experimental collaborators, the Biswell group, and we look at the structure of the silicon before and after cycling, we see that the p-pan and the pan, which bound with the bulk fairly strong to the interface, adhered well to the interface, they maintain their structure. So the silicon is not agglomerating into these larger particles, so we're not losing kind of the active surface area. Whereas polyaniline, we get a significant agglomeration because of that weaker binding, okay? And this happens as a bulk interfacial phenomenon, right? It's not, if we looked at just the chemistry of how one chain binds onto the surface, we would have missed this. So you really have to be able to scale up beyond just a kind of simple, a simple picture of looking at what specific bonds are forming. You need to understand the collective behavior at the interface. So other properties that we looked at, of course, with molecular dynamics, we can relax the bulk and we can squeeze the polymer and understand its mechanical properties. So here we found that the p-pan has the lowest Young's modulus. It's the most elastic. And again, this is a little bit counterintuitive. We would expect the chains of p-pan to be the least flexible because you have these aromatic rings, right? The pan, should be the most flexible because it's basically a chain that can spool itself up. The problem is that pan, it's so flexible that the chains get all tangled up. So that means collectively, you can't very easily stretch and compress because you have this tangled mess. Whereas the p-pan, the chains are less flexible. So they lie on top of each other, and that means that they can slide across each other a lot more easily. So again, the collective behavior is different than what we would expect from just a single chain. And then the final property we wanted to understand was the lithium conduction. Okay, so we did just a simple MD simulation where we have our equilibrated interface. We start with lithium, and we let the kind of lithium migrate through the system. And what we see is that the ordered interface of p-pan creates these channels that allows the lithium to get into and out of the system really fast. You don't get that with the pan and the polyaniline. So that ordered channel is really important for giving you the rapid ion conduction. And if we compare that, so this is just a picture of where the lithium is as a function of the simulation time. It gets closer to the surface faster for the p-pan. Experimentally, if we look at the measured lithium conduction rates, they're fastest for the p-pan. So again, there's some connection to the experimental observables. So the simulation really allows us to understand why the interface is so important, why the structure of the interface gives you the properties that are really essential for the battery performance, right? So we see that the collective behavior of the p-pan interface with silicon gives you the strongest adhesion. It gives you the best ionic conductivity because it creates these highways for the lithium. And also it's the most flexible. So the atomistic simulation is really giving us insight into experimentally why this particular p-pan binder outperforms some of the other binders. And we can then go back and use that to now design better binders for these composite systems. Okay, I will wrap up my talk there. And I'm happy to answer kind of any questions.
Okay, thanks very much, Tom. It looks like we have one question from Akash Kumar. Could you provide some information on the DFT computed silicon p-pan interfacial properties that were included in the development of the React's potential?
Yes, so the short answer would be we had to train the potential. If you go to our paper, we describe how we derived those parameters. I didn't include it in the talk because most people don't really want to hear about force field parameterization and fitting. But I'm happy to follow up with you after and really describe how we did it.
And also, do you see silicon defect evolution at these interfaces with time and temperature?
So we haven't looked at that. It would be hard. Well, so this is where even ReactFF being a cheaper computational method doesn't get us all the way away from the problem of being limited to nanoseconds and being limited to still only a couple thousand atoms. So it depends on what defects we want to look at. We haven't investigated that, but in principle, we could look at it, especially if it's something like vacancies migrating around or surface reconstructions that happen at relatively quick timescales.
Okay, thank you, Tom. And thanks again for the talk. So let's move on to our last speaker, Veronica Augustine. So Veronica is an associate professor of material science and engineering and a university faculty scholar at North Carolina State University. She's also associate editor for the Journal of Materials Chemistry A. Her research group focuses on the design, synthesis, and characterization of materials for electrochemical energy technologies. Veronica, please go ahead.
Okay, thank you so much for the introduction, and thank you to all the organizers for the opportunity to speak today on this energy storage webinar series. So I'm excited to be in the last speaker. I think I'm going to present something a little different, perhaps a little bit more on the materials, electrode materials perspective, and in particular, an area of research where we're looking at electrochemical reactivity under confinement that that really starts to think about the interface in a very atomistic way about what's going on in nanoporous materials. So first, of course, I want to introduce you virtually to my group. There's a lot of really fantastic folks who have contributed to this research, and in particular, I'll be sharing the dissertation research of Shelby Boyd, who graduated a couple of years ago from our group, Said and Mike Spencer, as well as postdoc fellows Simon Fleischman and Janelle Fortunato. We are very privileged to collaborate with a number of other wonderful folks that are listed here, and the research is sponsored through the Department of Energy, both an EFRC focused on fluid interface reaction structures and transport, as well as the DOE Early Career Program for the very last study that I'll share with you. So a little bit about our group. We are a material science group working in electrochemistry. So we really take a materials approach to understanding interfacial phenomena. It starts, of course, with material synthesis, and the kinds of materials that we're interested in are mainly transition metal oxides that are grown using solid state synthesis or solution chemistry type routes. This is an example of an electrodeposited film that I'll talk about later on in my presentation. And this is an example of a hydrated tungsten oxide material that I will not have a chance to talk about in this presentation. An important component of our work on electrochemistry of materials is, of course, getting them onto an electrode. And that can be as simple as just doing an electrodeposition reaction, as is shown here, where this is grown directly on a conductive substrate. But it can be more complex, especially if you're thinking about energy storage applications where you want high areal capacities or high volumetric capacities, and you start thinking about really optimizing ion and electron transport pathways through both the solid and the liquid state. And we have an ongoing project in this area on electrode architectures. Thick electrode architectures, I should say. And then underpinning all of our work is always this desire to understand electrochemical mechanisms, which includes these days operando techniques, in situ and operando techniques. We're pretty adventurous, I would say, in trying out different techniques. So it was really wonderful to see Irina's presentation earlier to think about new things to try, as well as coupling our experimental findings to computational results. And so you've seen on the previous slide, we do collaborate with a number of computational groups. So the title of this webinar is, where's energy storage headed? And as I was thinking about our group's research, I was thinking that really what we're doing, a lot of our work is thinking about where are energy storage materials headed, and in particular, intercalation materials. So right now they're used for energy storage applications. These insertion processes are the dominant mechanism by which we are storing energy in lithium-ion batteries. And of course, that's been a tremendous advancement that's occurring in the present day and will continue in the next few decades. Insertion processes, these very same insertion processes that we utilize for energy storage, are also used in some electrochromic windows based on transition metal oxides like tungsten oxides, which our group does a lot of work with. But what else can these materials do? It turns out there's quite a few things that I think are on the horizon the next decade or two, including using these materials as essentially sponges for the recovery of rare elements or separation of elements like capacitive desalination processes, using the electronic structure changes that occur during insertion for ion-based electronics, and even thinking about these materials as tunable electrocatalysts, where they are essentially electron and proton or electron and cation donating materials for subsequent interfacial processes that are occurring on their surfaces. So I think there's a lot that we can learn from insertion materials that is not only applicable for energy storage, but could also inform these new technologies. So if we think back to energy storage, why are insertion reactions so special? To me, the key thing is that they really optimize power and energy in the ultimate device. And on the materials level, what we mean is that they're optimizing the capacity or the degree of charge transfer that can occur with the kinetics limitations that can take place. And so this is kind of a landscape of different kinds of energy storage processes that can occur on electrode materials. The fastest processes, but the ones that yield the lowest capacities, are those associated with electric double layer formation, where there's only electrostatic interactions taking place, no charge transfer, very fast, a lot of cyclability, very little structural change in the materials, but we don't store a lot of charge. On the other extreme, we can have processes like conversion and alloying, where you have significant phase transformations taking place with high capacity. So if you can think about, for example, an oxygen, a bifunctional oxygen electrode, that's oxygen reduction, oxygen evolution. These kinds of mechanisms can provide a lot of capacity, but they're inherently more sluggish. Insertion processes are in the middle. They really are optimizing kind of the best of both worlds. And as a result, for energy storage, they're of interest not just for batteries, which is the most familiar energy storage type device, but also electrochemical capacitors. And these are the kinds of materials and processes that we're interested in. And in particular, from the standpoint of interfaces in our group, we asked the question of what happens when you have insertion materials that confine fluids, that contain water in their structure, where the distinction between an interface process like electric double layer formation and an insertion type process begins to blur. The starting point for a lot of this work is a perspective that I co-authored several years ago now with Yuri Gogotsi about what the opportunity could be for studying materials that confine fluids within their structure, essentially that they would bridge between the bulk layered materials, insertion materials like graphite and lithium cobalt oxide that are currently used in lithium-ion batteries, and the exfoliated nanoscale materials that are of interest for things like electrochemical capacitors. In this presentation, what I really want to kind of talk about is what happens when that distinction between liquid and solid is blurred, or when the electrochemical environment begins to kind of penetrate within the structure of a material. How does that help us understand electrochemical capacitance under confinement? And the story for this begins kind of interestingly with our desire to do a very practical project, actually, which was to understand how sodium metal oxides behave in aqueous electrolytes, because we wanted to see if they could be used for low-cost sodium ion batteries, as well as electrochemical desalination purposes. So first, in non-aqueous electrolytes, where many of us who study insertion chemistry are raised on non-aqueous electrochemistry, we have this gift in a way where, for the most part, for most systems, you can assume that what's intercalating into your electrode is a desolvated species. It's a desolvated cation There's a separation between what's happening in the electrolyte and what's happening in the electrode. This is all solid state. This is the liquid. There's an SEI that will form, but you can think about them as kind of two distinct phases. On the other hand, in aqueous electrolytes, you don't have this separation oftentimes. Water has a tendency to penetrate into your material. You don't have a solid degradation layer from your electrolyte. And so you really have to consider the likelihood of water infiltrating into a layered space, for example. So where we started the project is we said, okay, well, let's take a look at these P2 layered sodium metal oxides that are the most commonly used for non-aqueous sodium-ion batteries. It's a typical layered structure. You have edge-sharing MO6 octahedra. This is manganese rich, and you can change the other transition metals, usually third row transition metals, for cost and sustainability purposes. And in between these layers are sodium cations in a prismatic site. We put these things into an aqueous electrolyte, and what you see, this is neutral pH aqueous electrolyte, sodium sulfate. What we observed is that depending on the exact transition metal composition, we would observe either fairly reversible electrochemistry, and these are cyclic voltammograms showing sodium deinsertion and insertion into the material, or if we just slightly change the composition, we would see very, very different cyclic voltammetry, though the peaks that would disappear with cycling fairly quickly, that would become featureless in terms of any sort of specific potential dependence, and it become looking very capacitive. So an ideal capacitor in a cyclic voltammogram will look like a rectangle. This is not a perfect rectangle, it's tilted, but that could be due to things like ohmic polarization. So what's happening mechanistically in these materials, it turns out that the differences that we see between the first and second cycle, this potential dependence change from that occurs is really due to a structural transition, a very significant structural transition, an irreversible transition that takes place in the first cycle, where you take sodium ions out in the first cycle. If you take too much out, then what happens is very quickly you have a structural transition. This is just focusing on kind of the major peak that changes, which is this interlayer peak, where you form a hydrated phase. So the interlayer expands because water's going into the interlayer. As you can see, this is a very large change in the interlayer spacing, and that actually leads to a microscopic exfoliation and failure of the electrode because of such a large C-axis change. And so it's kind of disappointing, but this is the mechanism that happens. So to summarize, if we take these P2 oxides, you apply a high enough potential at some critical amount of sodium deinsertion, water comes in to the interlayer to offset presumably the negative charges between the oxygens, and you're ending up with this hydrated layered material. And if this happens on a slurry electrode, it's a failure, it's a degradation process, it's not great. However, we know that nanostructured bernstein, which has a very, very similar motif of edge-sharing MnO6 octahedra with water and cations in the interlayer, is used as an electrode material for electrochemical capacitors. So we decided to make lemonade out of a lemon, essentially, and say, okay, well, what if we do this process on powders of the material instead of on a slurry electrode, and try to make these expanded and hydrated metal oxides. So that's what we did. We placed a whole bunch of these P2 metal oxides into a pouch, apply a high voltage to drive sodium ions out of the material such that water will come in, and we form these beautiful micron scale particles that are now exfoliated and hydrated within their interlayer. Here's another picture of what that looks like. Really interesting materials. And now their electrochemistry is totally different. They behave exactly like capacitor materials, that rectangular cyclic voltammogram. The capacitive response actually is very similar to an activated carbon electrode, a state-of-the-art commercial activated carbon electrode that has 1,000 meters squared per gram surface area. The cycling stability is significantly improved. We didn't cycle for long. Electrochemical capacitors can go up to hundreds of thousands of cycles or more. This was just an idea that, this is very, very stable cycling that you can obtain. The prefixes here, the Fe and the Pe, just stands for whether we could obtain a fully expanded or a partially expanded material, which has to do with how well we can electrically connect all the particles in that pouch to drive sodium out of them. So this was a very interesting result for us, that we could take this kind of typical intercalation battery material and turn it into a very competitive material for electrochemical capacitors that now looks like a capacitor. And the question was, what's going on here? Why is this happening? What drives this process? And it led us to consider our understanding of electrochemical ion adsorption under confinement. So this is a picture on the left-hand side that is typical picture in an electrochemistry textbook, where we consider adsorption processes at a planar electrochemical interface. We can separate our ions into an inner Helmholtz plane where the ions are specifically adsorbed, or an outer Helmholtz plane where the ions retain their salvation shell and they're non-specifically adsorbed. And this, in a way, is what led to the distinction of different types of capacitances: double layer capacitance that's non-Faradaic in origin, pseudocapacitance that involves chemical bonding between a cation and the electrode. But what's going on in a material like the one I just mentioned, where we have water in the interlayer, is that you're now seeing a situation where the electrolyte is not just left cleanly at the outer surface. It's clearly penetrating into the structure. And we wanted to understand why this could be the case in an insertion process. Is there a transition from the double layer to a redox process like intercalation under confinement? And so we went and made burnasite itself, a very classic capacitive oxide. This is the structure of that material. This is the X-ray diffraction pattern showing its very nice layered structure. This is that electrodeposited film that I mentioned earlier. It's a material that's of interest not just for capacitors, for high power energy storage, but also desalination, as well as catalysis. When we talk about the capacitive response, that weak potential dependence, this is just showing you that it looks very similar to the micron scale electrochemically derived material that I just mentioned. The capacity is modest. It's about 35 milliamp hours per gram, or about 0.1 electrons per manganese that are being stored. Most of the capacity is coming from the potential independent process. So we can do a little bit of a cyclic voltammetry deconvolution into a perfectly rectangular response. And then this peak-shaped response, most of the capacity is obviously coming from that capacitive response. Both of these features are surface limited, so we see no mass transport limitations in the material. A question we had was, is this capacitive response just coming from the outer surface of the particles? So to determine whether that was the case or not, we cycled the material in a bulky cation electrolyte like tetrabutyl ammonium perchlorate in acetonitrile, so there was also no protons present. And what we found when we cycled it in this tetrabutyl ammonium perchlorate is that, which is unlikely to intercalate into burnasite because it's so large, is that the capacitance was orders of magnitude smaller than when we cycle it in an aqueous neutral pH electrolyte. It's about 10% of the total capacitance. And what that told us is that in these bulky cation electrolytes, there's no protons, no small cations present. We're just getting the outer surface adsorption process, but in the aqueous electrolyte, we must have insertion processes taking place as well. The next question, of course, was whether protons were also involved. So what we did here is we took our potassium sulfate electrolyte and added phosphate buffer, where now the buffer is a source of protons at a fixed pH that does not lead to the dissolution of the burnasite. And what we found is that while there's an initial increase in the capacity, so you can see that as an increase in the current at a fixed scan rate, there's very, very poor cycling stability in the buffered electrolyte, and that comes with dissolution. So what that means for us is that the capacitive process that we're seeing is really cation driven, and it's particularly driven by small cations like potassium. So the insertion part, whether we're getting insertion, was also verified through looking at the structural changes of the material, essentially the interlayer flexing or breathing during electrochemical cycling. And we did ex situ X-ray diffraction as well as in situ Raman spectroscopy that showed that we had this 1.4% interlayer change. And DFT simulations, this is where we have that nice opportunity to collaborate with computational groups, showed that indeed the magnitude of changes that we were observing could come from a mechanism whereby potassium cations, when they deinsert, are replaced by water molecules. And that leads to structural changes that are gradual and relatively small, with about 0.1 electrons per manganese distributed through. So a question that we had is, why does the cation intercalation appear capacitive? Why does it appear potential independent? And here's another example of where computational results come in. This is now the reactive force field grand canonical Monte Carlo simulations that were just talked about in the previous presentation. The gray atoms are the potassium cations coming into in between the Bernousite layers. And what you're seeing here is this beautiful exchange process of potassium with water molecules that essentially how we understand it is that the water that's confined in between the layers is mediating the distance between potassium and the oxide layers, leading to a non-specific insertion process. So what that means is that the potassium cations are not directly bonding to any particular site within the interlayer. They're localized perfectly in the middle. And that's why the cation insertion is capacitive. It's really due to the presence of that confined and disordered water network, so that the potassium insertion occurs right in the middle of the hydrated interlayer. There's even some partial solvation of that potassium by about 3 water molecules that surround it. It's non-specific, so the potassium is in the middle and distributes randomly. And most importantly, since it leads to very little structural change in the electrode, the water that replaces the potassium keeps layers from rearranging. And we think that's an important component of why this gives rise to very high cycling stability for this class of materials. It also wanted to touch upon really quickly the concept of electrochemical reactivity under confinement, which is kind of the next step, is now that we know kind of how ions and water molecules can organize themselves into confined spaces, can we look at subsequent electrochemical reactivity? And there's a lot of beautiful theoretical work done to suggest that this should be the case. You can do a number of things like change the physical properties of electrolytes or change adsorption behavior under confinement. We wanted to answer this question from a materials chemistry approach. And so to do that, we synthesized these hybrid tungsten oxide octylamine materials that essentially block the interlayer from reactivity. And what we found was that if you block that interlayer from being able to insert protons, you see a much higher overpotential for the hydrogen evolution reaction. So showcasing how important these cation insertion or proton insertion processes can be for interfacial reactivity. So with that, I'd like to conclude my presentation here and kind of say, this is some ideas for where energy storage materials are headed for energy storage applications, but also beyond, and what happens when we start to think about when the distinction between liquid and solid is blurred under confinement. I'd like to thank my research team again and our sponsors, and of course, thank you all for your attention.
Okay, thank you very much for your talk. So now I'd like to start the question and answer session. So first, I'm going to read the questions of everybody that's posted. And then once we're done with that, I'll ask some of those maybe more overarching questions that about electrochemical interfaces. So I'll just start from the top. So this is to Irina. How about solid liquid interfaces? Can GDOES be applied, and what info can it provide?
Very interesting question. So GD technique does have some limitations, because if you come to think of it, you need it creates a vacuum when your sample is pressed against the opening in the GD. To have that plasma, first it creates vacuum, then it generates plasma with the gas. So essentially, liquid will not be. Maybe if it's confined in pores, it can be okay, but liquid itself is not going to be possible. So it's only looking at solid-solid interfaces and bulk material composition.
Okay, thank you. And so another question for Irina from Emily Ryan. So wonderful overview of GDOES and your X-ray CT work. I'm curious about the temporal challenges. GDOES seems to be destructive in nature based on your overview, while X-ray CT is not. So GDOES cannot be used for operando characterization. Is that correct?
That's correct. So the GDOES is a destructive technique, and hello. I'm sorry. I think my connection was unstable for a second. So GDOES is a destructive technique. So yes, it cannot be used for operando studies. The way we use it currently, we pre-cycle battery to certain state of charge, we disassemble it, put it into this sample holder, transfer it to GD. First, of course, washing to eliminate any contaminants. And in terms of spatial resolution, of course, GD can resolve nanometer scale all the way to millimeter scale. So it's multi-scale in that aspect. In terms of temporal resolution that Emily mentions, and thank you, Emily, for such a great question, it's X-ray tomography. Currently can go into sub-second scans. You can have 3D image in sub-second mode. For battery science, I think this is not as interesting as for some other electrochemical interfaces, like where you have gas evolution, like electrolysis, or where you have formation of water, like water. Transient studies can be more interesting in those electrified interfaces. For batteries, I think because they operate closer to the equilibrium, a dynamic response is not as relevant. But yes, dynamic studies are possible, especially at several synchrotrons like Advanced Photon Source. It currently has the highest resolution, temporal resolution in America. In Europe, the Tomcat at the Paul Scherrer Institute has a capability of dynamic studies. Thank you.
Okay, so she actually has a long question, so there will be a few more. The next part of the question is that X-ray CT images seem like you were getting multiple images during charger. Would it be conceivable to image over multiple charge-discharge cycles?
So that's correct. So typically what's been done, we mount the cell on the rotating stage and we charge or discharge the cell. And during the scan, we stop the charging, just not to have any transient stuff happening. So yes, we typically do like during charge, maybe 4 scans, during the charge 4 scans, and that's done for identical locations. As we don't move the cell, we exactly see what happens in that location during both charging and discharging. And it's quite interesting because a lot of times you also see evolution of gas or some other side reactions that are typically probably would not be detected normally in electrochemical measurements, because if evolution of gases locally, it might not propagate into averaged electrochemical data that you collect. So it is identical location and we can do that, yes.
Okay, and then the last part to my question, she says about nucleation, the remaining lithium film that you would most likely seed the next round of dendrite formation. Is that the case?
If I understand the question correctly, yes, remaining QC would most likely seed. Yes, that's correct. That's correct. It's interesting because we see. I didn't show it here, but for example, for symmetric cell within the first 2 cycles, it matters which direction we played it, and we could clearly see. Okay, we played from here to here. We have pitting here. We have dendrites here. Then we strip back. So the history is preserved there, but then after like 5 or 6 cycles, we no longer see that which direction it was played at first. Everything is kind of averaged. You have both pitting and dendrites on each side, and that's what makes it interesting and complicated. So yes, Emily, that's right. The next layer of film will nucleate dendrites. That's right. Thank you.
Yeah, that's very interesting. Okay, so just to move on, so the next question is for Tom. For the lithium mobility, oh, this is from Jörg Erner. For the lithium mobility in the various p-PAN, PAN, and PANI polymers, did you include solvent polymer interactions like swelling of the polymers?
So we haven't done that, but that is exactly where we're heading next. Now that we know really how the silicon polymer interface is behaving, we want to start looking at the electrolyte, looking at the other side of this. So we're just starting that now. But that's, I think, one of, again, the advantages of ReactFF is we can build up this way and start adding in new elements, both in terms of what types of atoms, but also what components are in the system. So that's where we're heading.
Okay, great. So thank you, everybody, for answering those questions. And now I want to sort of throw out a question for all of the panelists to discuss, or a few questions. So one question that I have for you is, how can we have experiment and theory work more efficiently to address some of the lack of understanding of interfaces? Are there theoretical or experimental tools that you would like to see developed that would help you in your quest to better understand these interfaces?
Yeah. So it's always a challenge to find the connections between experiment and theory. And there's always a danger, as a theorist, if I see an experimental result, there's always a danger that I can, do a simulation that will support it or something. What I really think is a more fruitful way to work, and I try to tell my students to do this, is to be adventurous and go out on a limb, make a prediction, and then go ask, our experimentalist colleagues to go see if they can, if they can characterize it and understand, was the prediction really a prediction, or was it just a post hoc kind of rationalization? The challenge is length scales and time scales. And this is where we're using a variety of tools. So in the last talk, we saw, grand canonical Monte Carlo as a way to look at the thermodynamics of a system. And really that allows you to get away from the timescale issue if the physics are dominated by thermodynamics. There are some tools and tricks you can do with the kinetics to accelerate the molecular dynamics. I think those tools are essential, and they're constantly being developed and refined. And I think that needs to continue because it really allows us to connect the dots and bridge the scales.
And is there an experimental tool you'd really like to see made, so that they could help you with your simulations?
Yeah,
I guess within reason.
I think that knowing what is at the interface, and we heard about this in the first talk, because if I'm going to simulate something, I need to know what's really there. And if I come up with a model that I think is representative of the system, all the behavior that I see just depends on that first guess or that first, instinct. And having the solid characterization data at the beginning really makes my job a lot easier because I know I'm not going down the wrong path.
Mm-hmm. And Veronica, would you like to say?
Yeah, I wanted to chime in here if I can. I just wanted to say, as an experimentalist, I've worked with theory in different ways. Some has been in the way that I showed in my presentation, where we have scientific questions and then we work together with theory group to answer them, and they're really working on exactly the system that we're working on. And that's been really wonderful. That's facilitated through large center grants like EFRCs. There's really no other way to get that kind of work done. So thanks to the DOE for that. But there's other ways in our work on the last project that I talked about, in electrochemical reactivity under confinement. That's actually a field where I find most of the research is actually on the theory side. And what I find exciting for me is that what's difficult is to prove this experimentally or show this experimentally. And as a materials scientist, I think about, well, how can we design materials that could test out these hypotheses? A lot of them have to do with things like, your confinement geometry or your surfaces of the confinement. And I feel like we're in a place where the theory's done a fantastic job and has been very, very motivating for us to look into this area. And now we have more and more materials approaches. There's also really exciting materials like metal organic frameworks that you can design kind of bottom up to have these cage structures, and that's a very different way of using theory. And I'm excited about both opportunities. I think this is one of the most exciting things about doing science right now, is that there's multiple ways of kind of working with theory. Some can be in this very local, like direct interaction where you're working exactly on the same problem, and other times it's actually a group of theory that's been developed and is telling you there's something there, we can't prove it experimentally yet, we can't develop exactly the right tools or materials or whatever. You guys need to go after this.
And are there any tools you'd like to see built?
There's always tools to be built. All of
Nothing
the tools,
specific.
you know, that's that's the other fun part of electrochemistry, right? From the atomic scale to the micron scale and beyond, because we're talking about devices. So there is no shortage of tools that we can use.
Irina, do you have anything you'd like to add?
I think Tom and Veronica really did a great job answering this question, so I'll pass. Thank you.
So I guess from my perspective, being a person interested in first principles theory, it seems to me one tool could be linking the atomic scale to kind of the larger scale from MD to the experiments. And I guess in that sense, maybe that would help you figure out what's going on at those interfaces on the nanoscale. Okay, so maybe we have time for one more question. So another question is, what is a more significant challenge for in terms of how you can measure or model and also understand these interfaces, improving spatial or temporal resolution?
I mean, I can just briefly, I guess, answer that. So I think those are linked, and I would say spatial resolution, specifically when I talk about double layers and confinement, it's really very difficult to understand how do double layers look like. And there is a lot of studies on this, like in for example, electrocatalysis field, on the single crystals interfacing this idealized electrolytes, non-absorbing, and it's just even like understanding what is the double layer capacity. There is a lot of theories where you have the negative double layer capacity elements that are from between OHP and inner Helmholtz plane and metal, and trying to understand this whole double layer structure in both aqueous and non-aqueous solvents. I think it's a big challenge, and we want to do it in transient experiments, but even the steady state experiments currently, I think we need to better picture and better tools developed for that. And I think Veronica's talk really nicely motivated the problem and what they do and how to try to resolve this confinement effects. I think this is really next what we're going to see in future in a lot of other scientific works.
Veronica, would you like to say any last?
Yeah, no, I'm excited about it. I feel like this is the role of the microenvironment, the role of the nano environment is really talking about the organization of the solvents and ions and the electrolyte around heterogeneous electrochemical interfaces. And in the sense, that's more of a spatial resolution question, I think, to start with. But there are some really exciting things like cryo electron microscopy techniques. I've saw some beautiful double layer images of clay particles using scanning tunneling electron microscopy, as well as under cryo conditions. So, I think people really want to see these things. So spatial resolution to me right now is what comes to mind, more so than necessarily the temporal resolution, because I think from some spectroscopy techniques, we have the temporal resolution. Getting both obviously is the dream though, right?
Tom, any last words?
Yeah, I think, obviously, having both would be ideal. From a computational perspective, the spatial resolutions are going down experimentally, and that's great for us because now we know that we're modeling systems that are really representative of reality. And we see this in a bunch of different fields, like thinking about the coughs and the mops, right? We know exactly what those structures are. The temporal resolution is still a challenge for us, really being able to simulate something long enough to be sure that the system is relaxed away from whatever kind of artificial initial conditions we gave it. So, yeah.
Okay. Well, thank you, the three of you, our panelists, for joining us, giving excellent talks and excellent questions from the audience. Thanks also to our sponsors, ISC, College of Engineering, Division of Material Science and Engineering. It was a really interesting and illuminating workshop for me. So please join us again on February 11th. We're going to have the next of our series, which is on challenges of degradation and long-term operation. And then the final one will be February 25th. So thanks very much, everybody. And see you at the next workshop.
Thank you.